right, we're back. So, today what we're going to do is just a somewhat brief overview of different techniques that you can use to, or not so much the techniques, we've already got the techniques. So what I really want to say here is we're going to try to go over how do you recognize what techniques are likely to help you if you just encounter an integral. Now, the first thing I want to say is you want to remember all of the basic antiderivatives, and those are given on, if you look in Stewart, the textbook, on page 503, they have a nice little table there of all of the different antiderivatives that you want to kind of remember, ideally. At least, except for maybe 19 and 20, those are, well, you kind of want to remember those too if you can. But the point is, if you can remember all of those are sort of all of the different things that we know how to take antiderivatives. Sorry, 15 and 16, because we haven't really talked about hyperbolic functions in this class. So you can ignore the ones involving the hyperbolic trig, but everything else you do want to kind of remember and recognize if you need it. So the thing is, most problems to integrate are not going to be something that basic. Like, if I see the integral of secant squared, I can know immediately that that is tangent plus some constant of integration because the derivative of tangent is secant squared. But I'm probably not going to be lucky enough to just have a secant squared sitting there in the middle of my formula. So here is what I want to do. I want to kind of run through what are the different ways that you can, or what are the different steps that you should follow when you see an integral and you want to start working through it. So the first thing you want to do, sort of step one, is simplify as much as possible. So if there's any obvious simplification that you can do, you want to do it. Maybe there's something that you can take a product of. Maybe there's some kind of, some kind of a distribution. You may occasionally even want to factor something, but the point is you want to simplify. Oh, another thing you might be able to do is maybe you can use some kind of an identity. So maybe you can simplify your problem by using some kind of trig identity. I am going to borrow one example from the book here just to kind of show you an example of that kind of thing. So if I wanted to take, say, the integral of tangent theta divided by, let's say, secant squared theta d theta. Now, when I look at this, I actually first think, oh, it's too bad that secant squared isn't on top, because then I could do a u substitution. However, that is not the case here. It's on the bottom. So what you can do in these kinds of cases is you can think about simplifying this thing. You can think, well, what is this? Now, if I want to simplify this, usually I'm going to want to rewrite this in terms of sines and cosines. I can rewrite this as sine theta over cos theta. That's coming from my tangent. And then a secant squared in the denominator becomes a cosine squared in the numerator. But now the cosine squared is going to cancel with the cosine squared in the denominator here. So this leaves me with sine theta times cosine theta. And the nice thing about that is we know how to handle those back from 7.2, I think it was, trig integrals. Because we know that sine theta times cosine theta, well, this can actually be rewritten as 1/2 sine 2 theta. So this becomes 1/2 integral of sine 2 theta d theta. And now we can finish this off by a simple u substitution. We would substitute u equals 2 theta and then go from there. So at this point, we're kind of all set. And so that is sort of the first thing you want to do. See if you can maybe rewrite the problem in a way that is simpler. Now, the second step that you want to look for is going to be a regular substitution. Now, you may or may not be able to do one of these, but you want to kind of take a look and check. Because if there is something that is an obvious substitution, then you want to use it. And remember that the key is you're looking for a differential of some expression. So you need the derivative of something that is inside the function multiplied by dx. For instance, if I see something like the integral of x over x squared plus 4 dx, this x squared plus 4 might make me think of a trig substitution. Like if I just had 1 over x squared plus 4, this would make me think of a trig substitution. But in this case, because I have that x in the numerator, I can think, oh wait, this looks like if I take u to be equal to x squared plus 4, then du would be 2x dx, and I have an x dx here. So 1/2 du is equal to x dx, and I can rewrite this as the integral of, I'm going to pick up a factor of 1/2 here, and then I'm going to have 1 over u du. Now, if you've been following along the problems that we've been going over, if you've been thinking about, for example, a lot of the stuff we did with partial fractions, if you looked at some of those integrals we got last time, they involve things exactly of this form. Because what do you get if you do partial fractions with irreducible quadratics, like an x squared plus 4? Well, you end up with stuff like this together with stuff that looks like just a 1 over x squared plus 4. Now, of course, what would you do if you didn't have this x? Because if that x weren't there, you wouldn't be able to do this substitution. And by the way, I realize that today's lecture, we're going to kind of feel like we're going a little bit all over the place, but that's simply because I'm trying to show you some different examples here where we have to appeal to different techniques that we've learned. So we're not really looking at one specific technique. We're kind of looking at how do you look at something and recognize what to do with it. Well, supposing that I had something like the integral of, instead, 1 over x squared plus 4 dx. In this case, I recognize that this looks like an arctangent derivative, because the derivative of arctangent of x is 1 over x squared plus 1, I think. Now I'm going to double check here to make sure that I'm correct. Yeah, that is correct. So just making sure that I'm not lying to you here. Sorry about that. And so what I'm going to want to do here is I'm going to want to essentially factor out a 4. So I'm going to rewrite this as the integral of 1 over, let's see, this would be 4 times 1/2, I'm having a lot of trouble writing my parentheses today, 1/2 x squared plus 1 dx. And then you bring the 1/4 out, and you can now do a u substitution, u equals 1/2 x, and this turns out to be in terms of arctangents. So, once again, this should perhaps seem familiar to you if you've been thinking about the examples we did last time. Those integrals that we got, you can handle in this way. When you have an irreducible quadratic in the denominator, it will always come out to be something like this. And I can do the same technique if I have an irreducible quadratic, even if it's not just x squared plus 4. Because if I had something like, let's say I had the integral of 1 over x plus 3 squared plus 1 dx, maybe I get this because I did completing the square on the denominator. So if I didn't have the denominator written in this kind of form to begin with, I could complete the square on it. Well, then I can just do a u substitution of u equals x plus 3, and then this turns into an arctangent type of antiderivative. So those two examples are particularly relevant when you're dealing with partial fractions with irreducible quadratics, because those are the two kinds of antiderivatives that you will end up with when you're doing that partial fractions techniques. Okay, so what if there is no obvious substitution? Well, then we're going to need to do a bit more work, aren't we? Then we're going to want to ask ourselves, well, the first thing that I usually think about is, what about parts? Now, when is integration by parts going to be useful? generally speaking, it will be useful if you have something like a polynomial multiplying a transcendental function, like sine or cosine or e to the x or something of that nature, something that you can easily do antiderivatives of one of them, because we can do antiderivatives of things like sine x or cos x or e to the x fairly easily. What you want is you want one thing, one factor to be something you can do antiderivatives of easily, and you want the other factor to be something that as you take derivatives, it gets simpler and simpler until hopefully it will eventually become a constant. So if I have something like polynomial times t of x, so p here being a polynomial, t here a transcendental, which I'm just going to abbreviate here because I don't really have room to finish the word, then this is going to be something where integration by parts is going to work well. Sometimes, if you have two transcendental functions multiplying each other, you can also use parts and do one of those things where eventually you get back to the original integral, but you can then kind of solve for that integral. So we've seen that kind of thing before as well, where when you have two transcendental functions multiplied together, you can sometimes do a clever use of parts. But if you go back and you look at all the stuff that we did in the integration by parts chapter, that was chapter 7.1, you'll see that a lot of those examples are of this form, where we have a polynomial and a transcendental function multiplied together to give us our integrand. So that's the next thing you want to look for. Is there something where you can do this? The next thing that you want to think about, well, I'm kind of going slightly different order than the book is, I think, here, but the next thing you want to look at is if your function involves trig functions, well, then you want to go back and you want to do the stuff that we talked about with trig functions. So you either are going to be able to use a U substitution that we had, or you may have to use some trig identities to break things down. Like, remember, if we have an odd power of sine of x times an odd power of cosine of x, well, then we had to use some trig identities to break it down. But if either the sine or the cosine had an even power, then we were able to just use the Pythagorean identity and a U substitution to finish off the, if they were both even, that's when we need to use some complicated identities. If one of them has an odd power, that is when we can use the Pythagorean theorem together with U substitution, and it becomes fairly straightforward. And then we've got similar kinds of patterns that you want to remember with tangents and secants. So again, go back and look at 7.2, I believe it is, for examples of those kinds of things, and kind of get used to recognizing those patterns. This one's not too bad because you either have trig functions or you don't. It's not the kind of thing where you're confused about whether or not what you have is a trig function, hopefully. Hopefully you look at it and it either is or it isn't. So what is the next thing that we want to look at? Well, the next thing that we want to look at is maybe what we have is a rational function. So if it is a rational function, then we want to use partial fractions, which I'm just abbreviating as PF here. So partial fractions. And possibly before you do the partial fraction, you may have to do a polynomial division and turn this into a polynomial plus a rational function where the numerator is lower degree than the denominator. But that kind of comes back to step one of simplification. So, like, it's not as if these steps necessarily all always go in the same order. Sometimes you kind of go through and then you're like, oh wait, I have to go back and simplify more now in order to make this work. So if you have a rational function in there, then you're going to have to use partial fractions. Let's see. Then we have things where if I have a radical show up that looks like square root of x squared plus or minus a squared, square root of a squared minus x squared. In these types of cases, we want to do a trig substitution. That's the thing that's going to be most likely to help us out here. If you have something that looks like an nth root, then you can always try doing a u substitution of that nth root. And maybe what you end up with will work out for you, maybe not. It's actually, honestly, that one's kind of an annoying case. So, frankly, that one, unless you get very, very lucky, such an integral is going to be kind of really a pain to do. And I would strongly, I don't know, you're kind of in trouble if you get to that point. But you can always try doing a weird substitution where you just essentially substitute in the nth root of the function. I don't know what is going on in the hallway out there, but and see what happens. So those kinds of steps, they kind of give you your first best attempt. Now, what if you go through everything and it doesn't work? Because that can happen. Maybe there isn't really anything obvious to do after you go through this list. Well, then you kind of start over again. Are you sure you tried everything possible with substitution? Maybe there's another clever substitution. Now, there's usually only a few substitutions you could possibly try, so maybe just try them all and hope for the best. Integration by parts. Maybe it works in a way that you didn't necessarily see the first time. So keep trying it. See if you end up getting a repeating pattern that will end up working for you. You could try, instead of simplifying it, maybe you need to try rewriting it in a different way. So maybe you take your example and you kind of rewrite it in a way that is more complicated. So this is one where, let me erase this. Hopefully you guys have this down by now. And once again, I'm actually going to borrow this example directly from your book because I can't really think of a better one. So I don't like to do examples from the book too often since you have the book anyway, but I think this is one where it's actually kind of worth thinking about. If I have something that looks like the integral of dx over 1 minus cosine x dx, that doesn't really fall into any of the patterns that we've had so far that work nicely for me. But what I can sort of think about is, well, what if I sort of do something inspired by rationalization? Like, if this were some sort of a square root type thing, maybe I could try rationalizing this expression. And if I wanted to rationalize this expression, I would multiply by the conjugate. So I could say, well, this is actually the integral of 1 over 1 minus cosine x times 1 plus cosine x over 1 plus cosine x. And particularly what this is going to give me is on the bottom, this is going to give me a 1 minus cosine squared. And that is going to possibly simplify a bit for me and therefore hopefully be something that's a little bit simpler. So this is going to then become 1 plus cos x over 1 minus cosine squared x. Whoops, I'm sorry, I forgot my dx here. And then this is going to become the integral of 1 plus cosine x divided by sine squared x dx. Now, the nice thing about this is it splits into a cosecant squared x plus cosine x divided by sine squared x. And now we're sort of in a situation, the cosecant squared, that's easy. It comes out in terms of cotangents, negative cotangent, if I'm not mistaken here. And then this other one is more of the form where we can go back and use the techniques of 7.2 to work on it. So in this particular example, we were able to do this sort of clever manipulation here and get things to where we sort of recognize these integrals in terms of stuff that we kind of have seen how to do before. So that's one that you might be able to possibly do. Another example, and literally this is kind of what the book says at this point, is see if you remember doing something similar and if there was a trick that worked for that one. Because the truth is that as you build up experience with doing integrals, you will eventually start to recognize some patterns. And you might say, wait a second, I remember doing something almost exactly like this. And maybe I can use the same kind of trick here. Unfortunately, yeah, that just requires building up experience with integrals, and it doesn't really help you when you're first getting started. But eventually, maybe you just kind of recognize the patterns. And the final thing that you can try doing is essentially desperation. I'm being a bit facetious here, but just try everything that you can and see what happens. Okay, try rewriting stuff, try different tricks, try these kinds of tricks to rewrite it. You try everything, and essentially you just keep on trying it until hopefully something falls out. Now, the truth of the matter is that, you may have to use a combination of many methods. Maybe you have to do some kind of a rewrite, and then you have to do integration by parts. Or, I don't know, you could end up with all kinds of stuff that you have to do here in order to make this thing work. But eventually, you hope that you get down to where something is working for you. Some combination of tricks. So like I said, there's no real hard and fast rules, and this is what makes integration so annoyingly difficult. I'm going to tell you right now, I consider integration to be at least 20 times harder than differentiation. And there's two reasons for that. The first reason is because differentiation has a bunch of simple rules that you can follow. Like, you can just figure out derivatives by following a few basic rules. There's a lot more rules for integration than there are for differentiation. Like, there's a lot more different techniques in some sense. When it comes down to it, the only things you really need to memorize for derivatives are derivatives of sine and cosine and derivatives of e to the x, and everything else you can work out from those together with the basic rules for derivatives. But for integrals, that is not the case. Integrals are just a mess. There's, like a dozen different rules and things to memorize, and you have to memorize like 20 different antiderivatives, 16 different basic antiderivatives just to be able to get by. You can't just rederive those so easily on the fly. But the other problem is that with derivatives, it's always obvious what rule to use. Like, if I write down an example and I tell you, if we had been wanting to take, say, the derivative of 1 over 1 minus cosine x dx, it would be really easy to know what rules to use. We actually have two choices. We can either use the quotient rule, or we can think of this as the derivative of 1 minus cosine x to the minus 1. Why did I put a dx on there? Because I'm used to writing these integrals and I'm just confusing myself here. Just randomly writing dx's because I'm used to putting dx's on the end. And then we can use the chain rule. And both of these will give us the same answer. But the point is, there's a definitive, this is the rule you use. Maybe there's choices in which rule to use, but both rules are going to give me the answer, and that's that. But that is not the case with integration. There's no guarantees of which rules to use. I mean, there are some patterns that are so obvious that you know which rule to use. Like if I gave you something like the integral of sine cubed x cosine squared x dx, this one would have a fairly obvious, think of this as the integral of sine x times sine squared x cosine squared x dx, and do a u substitution, u equals cosine squared x, use the Pythagorean theorem to get sine squared in terms of cosine squared, and you're done. So like there are some where the rule is sort of jumping out at you, at least once you've gotten enough practice with this, but it's not as simple as, oh, we have a quotient, we can automatically apply the quotient rule, or oh, we have a composition of functions, because I can think of quotients as compositions this way, we can apply the chain rule. It's not as straightforward where these techniques will automatically work, right? Because for instance, if I instead of cubed had this as squared, well, now that almost looks identical, but it doesn't work at all the same. We have to go through and we have to use those half and double angle identity things to simplify this out now. So the point is that taking integrals is a lot harder. Now here's what I'm going to recommend. Instead of me just showing you a few examples on here, I want you to make sure that you take a look at all of the different examples on pages 505, 506, and 507. Well, I guess the examples kind of stop at 506 now that I'm looking at it, but make sure to take a look at those examples in your book. And then also, I'm going to post like lists of examples for you to look at. And once again, I'm going to encourage you to work through those examples yourselves and then read the solutions if you get stuck, or to double check that you've done them correctly. So the best way to handle this is really to just do them yourselves. And this is something that if we were doing this in the in-person setting, we could, I could just give you some problems and ask you to work them with me, and I could kind of walk around and help you with it and things like that. But because we don't have that, we're going to do the alternative here of I'm going to give you resources online for your supplemental readings, and you can read through those examples, and those will kind of serve as a guide to this is what you want to try in these kinds of cases. Because that's really the problem here. The most that we can give you is a guide. We cannot give you this rule will automatically always solve the problem for you no matter what, okay? It's not quite like that. And this is why antiderivatives are so difficult. Like, you can program a computer to find antiderivatives for you, no problem. You cannot program a computer to find antiderivatives for you, no problem. Actually, things get even worse. So the thing is that the derivative of a function built out of polynomials and transcendental functions and radicals, that will always have another derivative that can be written in terms of polynomials, radicals, and transcendental functions. Well, the antiderivatives, not necessarily the case. Let me show you actually a really simple example that it looks like we ought to be able to do. It's a really important example. It turns out we cannot do it. If I wanted to do the antiderivative of e to the x squared dx, this does not have what is called a closed form solution. You cannot find the answer to this just in terms of a nice combination of transcendental functions and polynomials and things. And yet it's such a basic example here. Actually, the one that is even more important is e to the minus x squared. Because what is e to the minus x squared? Well, it's a scaling of the Gaussian distribution. And the Gaussian distribution is really important in statistics, in physics, in all kinds of applications. Well, it turns out, yeah, but the Gaussian distribution cannot be integrated to give you a closed form antiderivative. I can't just write down, here's a function given as an expression involving polynomials, transcendental functions, and radicals, and rational functions, and things like that. You can't do that. Now, you can figure out what this comes out to be in some other ways, and we will talk about some of those other ways later. It turns out, for example, we can give a series solution to this. It turns out that if you wanted to do some certain types of definite integrals, for example, if I wanted to do this integral from minus infinity to positive infinity of e to the minus x squared dx, turns out there are tricks for solving this, although they are by no means obvious at all. It turns out that in order to do this, you actually have to use techniques from Calculus 3 or from complex analysis. So, still very difficult. The point is, integration is hard, okay? And so I don't want you to feel like, I know I've been saying this for about 5 minutes now, but I don't want you to get discouraged if you encounter problems that are confusing. Yeah, they are confusing. They're not easy. This is tricky stuff. So again, I'll be posting the information for those things online that I want you to look at, these worked problems. I want you to try to do those yourselves, and then check how the problems have been worked out, and then let me know if you have any questions, because I can always help you out with that. But I think that's going to be more useful than just watching me do a few examples up here. So yeah, I'll be posting that soon, and talk to you later.